Welcome back, everyone, to the Deep Dive. Today, we're going to be looking at something that's kind of invisible, but super important in the world of mobile apps: how our phones deal with network information.
It's everywhere, right? Like you're constantly scrolling through Instagram, downloading podcasts, checking the news. Your phone is always talking to the internet, and there's a whole system for managing all that chatter.
It's pretty wild when you think about it, like all that data flying back and forth constantly.
Yeah.
And for developers building these apps, making sure the communication works smoothly is really crucial for a good user experience. No one wants a laggy app.
Yeah, exactly. And in the mobile world, that connectivity is even more vital because these devices are designed to be on the go. So it's not like a desktop that's always plugged in. You're moving between Wi-Fi and cellular networks, maybe even dealing with intermittent connections.
So it adds a whole extra layer of complexity. And that's what we're going to be unpacking today. We're going to be focusing on the Android platform based on the materials we've got. We'll be exploring how mobile devices handle accessing data, managing those background tasks, and really importantly, keeping things running smoothly without everything freezing up. We've got some great resources to dig into, so let's get started. Okay, one of the first things that jumped out at me is this hard and fast rule about network operations on Android. You absolutely cannot, under any circumstances, perform operations that fetch data on the main thread. Why is that such a big no-no?
Well, the main thread, sometimes called the UI thread, is kind of like the control center of your app. It's responsible for handling all the user interactions, the animations, drawing the screen. Basically, it's what keeps your app feeling responsive.
Yeah, it's what makes the app feel snappy and interactive.
Exactly. Now, imagine what happens if you start making network requests on that main thread. Those requests can take time, sometimes a lot of time, especially if you're on a slow connection. And while the main thread is waiting for those requests to finish, it can't do anything else. It gets totally blocked.
Oh, so that's what causes that dreaded app freezing or the app not responding message.
Exactly. And to prevent that from happening, Android throws an exception, a network on main thread exception to be precise. It's like the system saying, hey, you're doing something dangerous here, stop it.
So that's like a built-in safety net.
Yep, it protects the user experience, and it also guides developers towards the right way of doing things, which is keeping all network operations off the main thread and in the background.
Right, so golden rule number one, network stuff happens in the background, not on the main thread. And speaking of network access, before you can even make those requests, you need special permission from the system, right? It's not just open season on the internet.
Yeah, that's right. You need to explicitly declare that your app needs internet access. And you do that by adding a specific line to your Android manifest.xml file. It's a line that says, uses -permission android.name, android.permission.internet. This is like asking the user, hey, is it cool if I use the internet? It's a basic security measure to ensure that apps aren't just silently using data without the user knowing.
It's like good digital manners, asking permission before you start using the internet. Makes sense. Now, let's say you want to display web content directly within your app, like embedding a web page or a web-based form. There's a specific component for that in Android, the web view. What can you tell us about that?
So the web view is really cool. It essentially allows you to embed a mini web browser right inside your app. So you can display HTML content, whether it's a full web page from a URL, a formatted document, or even just a small part of a web-based user interface. It's really versatile for integrating web experiences into your native app.
It's like having a window to the web right there inside your app. And one thing I found interesting is that JavaScript execution is disabled by default in a web view. Why would that be? Why not just let JavaScript run freely?
Yeah, that's an important security consideration. See, JavaScript can be very powerful, but it can also be used for malicious purposes. If you're loading content from a trusted source, enabling JavaScript is usually fine. It lets you have interactive elements and dynamic content. But if you're loading content from an untrusted source, enabling JavaScript could potentially open up your app to security vulnerabilities.
So it's like, if you don't trust the source, it's better to err on the side of caution and keep JavaScript turned off.
Exactly. It's better to be safe than sorry when it comes to security. And if you do need to enable JavaScript, you can do so through the web view settings. It's all about making conscious and careful decisions as a developer.
So there's this whole balance between functionality and security.
Yeah, finding that right balance is key. And speaking of the web view settings, there's a method called getSettings that gives you access to, well, the settings.
I imagine that's pretty important for customizing how the web view behaves.
It is. The getSettings method returns a web settings object. And this object is like your control panel for everything related to how the web view works. You can enable or disable JavaScript, manage caching, control zooming, set user agents, and a whole bunch of other configurations. It gives you really fine-grained control over the web content you're displaying.
So it's like fine-tuning the web experience within your app.
Precisely.
All right, and then we've got a couple other key methods.
Right.
Load URL and load data. What are these used for?
So load URL is the most straightforward way to load content into a web view. You simply pass it the URL of the web page you want to display, and the web view will take care of fetching the content and rendering it. It's like typing a URL into your browser.
Easy peasy. And what about load data? When would you use that?
Load data is for when you already have the HTML content as a string within your app, and you want to display it in the web view. This can be useful if you're generating HTML dynamically or if you've bundled some HTML content directly within your app.
So one is for fetching content from the web, and the other is for displaying HTML you already have.
Okay, that makes sense. Now let's shift gears a bit and talk about how our app can actually reach out and grab data from a server. The core mechanism for that is the HTTP protocol, and our sources point to the java.net package in Java.
Right, the java.net package provides all the fundamental classes for network communication in Java, which Android builds upon.
Yeah.
It's got everything you need to make network requests, handle responses, work with URLs, and so on.
And HTTP is kind of like the language of the web, the way browsers and servers communicate, right?
Exactly. It's the set of rules they follow to exchange information. And when we were talking about web addresses, the URLs that point to specific resources on the web, we use the URL object in Java to represent those.
Makes sense. So it's like a digital address book. Now, when it comes to actually making those HTTP connections, our sources mention two main types: HTTP URL connection and HTTPS URL connection.
They sound very similar. What's the difference?
The key difference is security. HTTP URL connection handles regular, unencrypted HTTP connections. This means that any data transmitted over this type of connection could potentially be intercepted by someone snooping on the network.
Oh, that doesn't sound good.
Not ideal, especially if you're dealing with sensitive information like passwords or credit card details. That's where HTTPS URL connection comes in. It uses something called TLS-SSL encryption to secure the communication channel.
So it's like putting a lock on the data being transmitted.
Exactly. With HTTPS, the data is scrambled during transmission, and only the server with the right key can unscramble it. This prevents eavesdropping and makes sure the data is protected.
So in most cases, especially when dealing with any kind of personal or private information, you'd want to use HTTPS URL connection, right?
Yeah, pretty much always. These days, security is paramount, and using HTTPS is just good practice.
Our material also briefly mentions the concept of sockets for network communication. How do sockets fit into all of this? Are they an alternative to using URL connection?
So HTTP URL connection and HTTPS URL connection are like high-level abstractions built on top of sockets. They handle a lot of the complexity of the HTTP protocol for you, making it easier to make web requests. Sockets, on the other hand, are lower level. They give you more direct control over the network communication, but they also require you to handle more of the nitty-gritty details.
So it's like the difference between driving an automatic car and a manual car.
Yeah, that's a good analogy. With URL connection, you're basically telling the system, hey, I want to make this web request, take care of all the low-level stuff for me. With sockets, you're more involved in the process, like manually shifting gears and controlling the engine.
Okay, so for most common web interactions, the URL connection classes provide a much simpler and more convenient way to go.
Right, and the URL connection classes are specifically designed to work with the HTTP and HTTPS protocols, which are the standard for web communication.
All right, so let's say we're using HTTP URL connection to fetch some data from a server. What are the steps involved in making that happen?
So the first step is to create a URL object, pointing to the web address you want to access. It's like typing the website address into your browser.
Setting the destination.
Right. Then you call the open connection method on that URL object. This establishes a connection to the server and returns an HTTP URL connection object, which represents that active connection.
So that's like dialing the phone number.
Exactly. And once you have that connection, you might need to send some information to the server as part of your request. This could be data from a form, some parameters you want to pass, or whatever else the server expects.
So that's sending our message or a data.
Right. Now, once you've sent the request, the server is going to send back a response. And one of the first things you want to check is the response code. This is a 3-digit number that tells you the outcome of your request.
So it's like the server's way of saying, hey, I got your message and here's what happened.
Precisely. The most common response code you'll see is 200, which means everything went well, and the server is sending back the data you requested.
That's the good one, the green light.
Exactly. But there are tons of other response codes indicating different things like errors, redirections, or other situations.
So you need to pay attention to those response codes to make sure your app is handling things correctly.
Absolutely. And finally, if the request was successful and the server is sending back some data, you can access that data as an input stream by calling the getInputStream method on your HTTP URL connection object. This input stream is a stream of bytes that represents the data coming back from the server.
So the input stream is the pipeline carrying the data.
Exactly. It's the raw data that your app needs to process.
Now, once we have this raw data, what do we actually do with it? Our sources talk about handling it as raw bytes or converting it into text. What are the options?
Yeah, so it depends on what kind of data you're expecting. If it's binary data, like an image or a video, you might work with the input stream directly as a stream of bytes. But if it's text-based content, like HTML, JSON, or XML, you'll need to convert those bytes into characters and strings that your app can understand.
So it's like translating the data into a language our app can speak.
Exactly. And for that conversion, we have a few tools at our disposal in Java. There's Input Stream Reader, Buffered Reader, String Builder, and String Buffer.
Okay, those are some familiar names, but can you give us a quick rundown of what each of those does?
Sure. So Input Stream Reader takes the raw bytes from the input stream and converts them into characters based on a specific character encoding, like UTF-8, which is commonly used for web content. Buffered Reader then wraps that Input Stream Reader and adds a buffer, which makes reading the data more efficient. It's like reading a book with a bookmark. It helps you keep track of where you are and read smoothly.
So one decodes, and the other helps us read the data efficiently. And what about String Builder and String Buffer?
Those are used for building strings, especially when you're dealing with data that comes in chunks, like from a network stream. String Builder is more commonly used because it's generally faster, but String Buffer is thread-safe, meaning it can be used by multiple threads at the same time without causing problems.
So they help us assemble the pieces of text we get from the network into a complete string that we can then use in our app.
Exactly.
Okay, that makes sense. Now, all this back and forth communication with the network can take some time. And that brings us to the crucial concept of asynchronous operations. Why are these so vital in mobile apps, especially when dealing with network requests?
Asynchronous operations are all about keeping your app responsive. Remember, if you do something that takes time, like fetching data from the network, on the main thread, your app freezes up. The user can't interact with it, and it's a terrible experience. Asynchronous operations allow you to offload these long-running tasks to separate threads, so they happen in the background without blocking the main thread.
So the main thread can keep doing its thing, handling user interactions and keeping the UI smooth, while these other threads handle the network stuff.
Exactly. And that's what makes an app feel fast and fluid.
Right. No one wants an app that feels like it's constantly lagging or getting stuck. Now, our sources highlight a couple of common challenges when working with these background operations. One is passing data in and out of those background threads, and the other is updating the UI with the results once the background work is done. Can you elaborate on that a bit?
Yeah, so because those background threads are running independently from the main thread, you can't just directly access UI elements or share data between threads without potentially causing problems. It's all about having controlled and safe ways to pass data between threads. For example, if you want to update a text view with the data you fetched from the network, you can't just do that directly from the background thread. You need to send that data back to the main thread somehow, and then update the UI from there.
So it's all about thread communication and synchronization.
Exactly. You need to make sure that the right data is going to the right place at the right time, and that everything is happening in a synchronized way that doesn't cause conflicts or crashes.
Okay, that sounds tricky. So how do we actually achieve this asynchronicity in Android? It looks like there are both standard Java ways and Android-specific approaches. Let's start with the Java fundamentals, the thread class, and the runnable interface.
Right. Those are the building blocks of concurrency in Java, and they're used extensively in Android as well. A thread represents a single stream of execution. It's like a worker that can execute a task. And the runnable interface defines what that task is. You create a class that implements runnable, put the code you want to run in the background inside its run method, and then create a thread object passing your runnable to it. Finally, you call the start method on the thread, and that kicks off the background task.
So runnable is the job description, and thread is the worker who carries it out. And our sources mentioned that each thread gets its own instructions, registers, and a stack. What's the significance of that?
Well, those things, the instructions, registers, and stack, are essentially the resources that a thread needs to execute code. And the fact that each thread has its own set of these resources means they can run truly in parallel. It's like having multiple workers, each with their own tools and workspace.
Right, so they're not stepping on each other's toes.
Exactly. And this parallel execution is what allows your app to do multiple things seemingly at the same time, like downloading data in the background while still responding to user interactions on the main thread.
Our sources give a great example of a web browser using threads to download a file while simultaneously displaying the parts it has already received. That's a perfect illustration of how multi-threading can make an app feel much smoother.
Yeah, it's a great example. If the browser had to wait for the entire file to download before displaying anything, it would feel really slow and unresponsive. But by using threads, it can keep the user informed about the progress and make the experience much more pleasant.
And that responsiveness is key in any mobile app, but especially in apps that are heavily reliant on network communication. Okay, let's walk through the steps of creating a new background thread using thread and runnable. We've talked about declaring a runnable and defining its run method, then creating a thread object and passing the runnable to it. What happens next?
The final step is to call the start method on the thread object, and this is where the magic happens. Calling start doesn't directly execute the run method on the current thread. Instead, it tells the operating system, hey, I want to create a new thread, and when that thread starts running, execute this run method.
So it's like giving the worker the signal to start working.
Exactly. And once the thread starts, it will execute the code inside the run method, and then it will terminate when the run method finishes.
Okay, so that's how we create and start a background thread. Now let's talk about that communication challenge we mentioned earlier. How do we get data back from the background thread to the main thread so we can update the UI? Our sources point to handler objects as the key mechanism. Can you explain how they work?
Sure. So a handler is basically a message handler. It's associated with a specific thread, and it can receive messages and runnable objects from other threads. And those messages and runnable objects will then be processed on the thread that the handler is associated with.
So it's like a designated messenger that can deliver messages between threads.
Yeah, that's a good way to think about it. And the way it works is that each thread has a message queue. And when you send a message or a runnable to a handler, it gets added to that thread's message queue. The handler then processes those messages and runnable objects one by one on the thread it's associated with.
So if we want to update the UI from a background thread, we create a handler that's associated with the main thread and then send our updates to that handler.
Exactly. And that handler would then take care of updating the UI safely on the main thread. It's a really powerful mechanism for ensuring that UI updates happen on the right thread.
Okay, that's a clever system. Now, our sources also talk about AsyncTask, which is described as a helper class built on top of thread and handler. It sounds like it was meant to simplify the whole background task management process.
Yeah, AsyncTask was created to streamline the common pattern of doing some work in the background and then updating the UI with the results. It was really popular for a long time, but it's actually been deprecated in more recent versions of Android.
Oh, so it's not really recommended anymore. Why is that?
Well, it had some limitations that could lead to problems, especially in complex apps. It could be tricky to manage the life cycle of async tasks, especially when dealing with things like screen rotations or activity life cycles. And there were some potential memory leak issues that could arise if async tasks weren't handled carefully.
So, while it was a helpful tool for simple cases, it had some hidden complexities that could cause headaches down the line.
Exactly. And that's why the recommendation has shifted towards using more explicit thread management with thread and runnable, or using higher level abstractions like the Executors framework.
All right, let's talk about AsyncTask a bit more, just for historical context. Our sources say that we need to implement an abstract class, AsyncTask params type, progress type, result type. What are those type parameters all about?
So those type parameters specify the types of data that your async task will be working with. Params type is the type of input you pass to the background task when you start it. Progress type is the type of value you use to report progress updates. And result type is the type of the final result that the task produces.
Okay, so it's like defining the input, the progress updates, and the final output.
Right. And then you have to override a few lifecycle methods to define what actually happens during those different stages.
Let's go through those methods. We have on pre-execute, do in background params type.params, on progress update, progress type.params, and on post-execute, result type param.
All right, so onPreExecute is the first method that gets called, and importantly, it runs on the UI thread. This is where you do any setup work before the background task starts, like displaying a progress dialog or initializing some UI elements.
So it's like the preparation phase.
Yeah, getting everything ready. Then we have domain background, params type.params, which is where the actual heavy lifting happens. This method runs on a background thread, so it won't block the UI. And this is where you put all the code for your long-running tasks, like fetching data from the network, processing images, or whatever it might be.
So this is where the real work happens, in the background.
Right, and this method receives the input parameters you passed to the execute method, and it has to return a result which will be passed to the next stage. Now, if you want to provide progress updates while the background task is running, you can call the publish progress method from within do in background.
So you're sending updates from the background thread.
Exactly. And those updates will be received by the onProgress update, progress type.params method, which also runs on the UI thread. So this is a safe place to update UI elements based on the progress of the background tasks, like updating a progress bar or displaying a percentage complete.
So publish progress sends the updates, and onProgress update handles them on the UI thread. Makes sense. And finally, we have onPostExecute result type param, which runs after do in background finishes.
Right. OnPostExecute runs on the UI thread and receives the result that was returned by do in background. This is where you typically update the UI with the final results of the background task, like displaying the fetched data, showing a success message, or handling any errors that might have occurred.
So it's the final act, wrapping things up on the UI thread.
Exactly. And to kick off the whole process, you call the execute method on your AsyncTask object, passing in any input parameters you need.
Okay, that'll make sense. It's a nice structured way to handle background tasks and UI updates. But you mentioned that AsyncTask has been deprecated. What are the recommended alternatives?
Well, the most common alternative is to use the Executors framework. This is a more powerful and flexible way to manage threads in Java. It allows you to create thread pools, schedule tasks, and control the execution of your background operations in a more fine-grained way.
So it's like having a team of workers that you can manage and assign tasks to.
Yeah, that's a good analogy. And when you use Executors, you typically combine them with handler objects to handle communication back to the UI thread. It's a really powerful combination that gives you a lot of control over your background processing.
Right, that's a lot to take in. We've covered the basic rules of network access, the different ways to fetch data from a server, and the importance of asynchronous operations for keeping our apps responsive. It's clear that understanding these concepts is essential for building any mobile app that interacts with the network.
Absolutely. And as mobile apps continue to evolve and become more complex, these concepts will only become more important. It's all about creating apps that are fast, fluid, and provide a great user experience.
And I think what's really fascinating is how all these mechanisms we've talked about, the creation of threads, the handling of messages, the communication between threads, all this stuff is happening behind the scenes, invisibly to the user. But it's what makes all the amazing features we take for granted in our mobile apps possible. Everything from streaming music to getting real-time traffic updates all relies on these fundamental concepts.
That's right. And as we move towards even more data-driven and connected apps, the way we handle concurrency and network communication will continue to be crucial for creating apps that are both powerful and enjoyable to use.
So for all you listeners out there, think about all the apps you use every day and how they seamlessly manage to do so much in the background without ever making you wait. It's all thanks to these powerful techniques. And as you continue to explore the world of mobile development, keep these concepts in mind. They're the foundation for building apps that are truly world-class. We've included links in the show notes to some great resources on Java concurrency, the Executors framework, and even AsyncTask if you're working with legacy code. Definitely check those out if you want to learn more. Thanks for joining us on this deep dive. Until next time.